So hello my dear students, today we are going to start with unit number 3, that is diagonalization. So let us try to understand the definition of diagonalization first, and then slowly and steadily we will move towards the examples. So it's my request to you that pay proper attention, because each and every concept is important. Then and then only you will understand the examples based on diagonalization. Obviously it is not completely a new topic. Whatever concept we have discussed in unit number 2, that ideas have been extended over here, and the new topic has been formed, that is called as a diagonalizable matrix. But before that, let us study what is a diagonalizable linear transformation, and then we will go forward diagonalizable matrix. Okay, so note, we should have a finite dimensional vector space, then a linear transformation from V to V. Note, domain and codomain is same. Linear transformation T from V to V is said to be diagonalizable if there exists a basis of vector space V with respect to which the matrix representation of T is a diagonal matrix. The definition is very simple and straightforward. You already know that every linear transformation can be written in a matrix form. Obviously we need some basis for that. So over here the definition is saying a linear transformation from V to V is diagonalizable if there exists a basis of V with respect to which the matrix representation of T is a diagonal matrix. Now this basis need not be unique, means one student may get different basis of other student may get different basis. Okay, but if you are able to find such a basis that converts our linear transformation to a diagonal matrix, then we will say that our linear transformation is diagonalizable. Now the next thing is, but it is quite vague concept. I mean, it is very difficult to show that certain linear transformation is what diagonalizable. So therefore there is one note. So a linear map is said to be diagonalizable if V is having a basis consisting of eigenvectors of T. Okay, so this is simple definition now. Okay, so in other words, you can say that a linear transformation is diagonalizable if V is having a basis consisting of eigenvectors of T. Now every linear transformation obviously from V to V is going to have eigenvectors, and if that eigenvectors is forming a basis for the vector space V, then we will say that the T is diagonalizable. Then how to decide it? Idea is simple. If your vector space is having the dimension n, then we need how many eigenvectors? We need n eigenvectors in the basis set of V. So if you are getting n linearly independent eigenvectors corresponding to that linear transformation, then definitely it is going to form what basis of the vector space V, and your T will be what diagonalizable. It's very simple definition. Okay, and if your linear transformation is having less than n vectors, let me say less than n eigenvectors, then there is no point of there is no point that eigenvectors will form a basis of V, because we will need n eigenvectors, isn't it? N linearly independent eigenvectors in fact. But the important concept for us is diagonalizable matrix right now, so we will focus on that. So definition of that is also simple. A square matrix A is said to be diagonalizable if it is similar to a diagonal matrix. Now we already know that how the two matrices are similar, right? So the thing is, now a square matrix will be diagonalizable if it is similar to a diagonal matrix. It makes sense, right? Therefore the matrix is said to be diagonalizable, therefore the word diagonalizable. Okay, but what do you mean by similar to a diagonal matrix? It means that there should exist a non-singular matrix P such that P inverse AP should be equal to D, where D is a diagonal matrix. Now the question is how to find that non-singular matrix P. We will see that while discussing some examples, then you will get the idea. So right now just keep it in mind, a matrix will be diagonalizable if it is similar to what a diagonal matrix. Means there should exist a non-singular matrix P such that P inverse AP should be equal to D, that is where D is what a diagonal matrix. Now the thing is, how to decide that a certain matrix is diagonalizable or not? There are some short tricks in order to decide it. The first trick is, if your matrix is having a distinct eigenvalues, then directly you can say that that matrix will be diagonalizable. Now you will say how it will be diagonalizable if it has distinct eigenvalues. Okay, that you will understand if we see some examples. Okay, so when I will explain the examples, at that time I will tell you why our matrix is diagonalizable if it is having distinct eigenvalues. Okay, there is very simple reason for that. So that is what note I have written here. So if A is your real matrix and lambda 1, lambda 2 up to lambda n are distinct eigenvalues, then A is what? Diagonalizable. Okay. Now the next thing comes algebraic multiplicity of eigenvalue. Now we have already learned the concept of eigenvalue. Now what do you mean by algebraic multiplicity? It is very simple. We have already seen before the concept of multiplicity of a root. So actually eigenvalue is nothing but what? It is a root only, right? So actually algebraic multiplicity of eigenvalue is nothing but number of times that eigenvalue appears as a root of characteristic equation. I mean, suppose your matrix is having eigenvalue, suppose order of the matrix is 3 and eigenvalues are 1, 1 and 1. So all the eigenvalues are, there is only one distinct eigenvalues, I mean eigenvalues are repeated. So this one eigenvalue is repeated how many times? 3 times. So therefore the algebraic multiplicity of this eigenvalue is 3. Okay, algebraic multiplicity of the eigenvalue 1 is 3. Now if your eigenvalues are 1, 1, 2, then what will be algebraic multiplicity of the eigenvalue 1? Then it is going to be 2. And what will be the algebraic multiplicity of the eigenvalue 2? It is going to be 1, because it is appearing only once as a root of what? The characteristic equation. And this is nothing but what? The algebraic multiplicity. Now next is geometric multiplicity of an eigenvalue. So what is geometric multiplicity of an eigenvalue? That is also simple. Now we have already learned how to find the basis of the eigenspace, right? So you simply see the number of vectors in the basis of the eigenspace. Now as I am saying number of vectors in the basis of the eigenspace, immediately in your mind you might think of the concept of dimension, and you are absolutely right. Okay, so actually geometric multiplicity of eigenvalue is nothing but what? The dimension of the eigenspace of lambda, of the eigenvalue lambda, is nothing but the geometric multiplicity of the eigenvalue lambda. It means if your basis of the eigenvalue lambda is containing 2 vectors, then our geometric multiplicity is going to be 2. Okay, and depending upon it there is one theorem. Okay, now keep in mind that the definitions of algebraic multiplicity and geometric multiplicity, I am assuming that they are clear now. Okay, so now we will move towards the next one. There is one important note actually, that your geometric multiplicity is always less than algebraic multiplicity. So therefore we say that geometric multiplicity of an eigenvalue does not exceed algebraic multiplicity. Okay, so actually this is a theorem, but we are going to see the proof afterwards. Okay, so in this way you can remember GM is always less than AM. Okay, that is geometric multiplicity is always less than AM. You can say grandmaster is always less than arithmetic, whatever you can say. You can apply your own logic. I used my own logic when I was in college to remember it. Okay, so you can also use some trick. See, students get confused. Remember, so I remembered my name starts from G. Okay, so therefore GM is less than AM. So anyway, you can use your logic and you can remember it. Okay, yeah. The next note is, if your matrix is satisfying the condition A square is equal to A, I mean if your matrix is idempotent, so this condition A square is equal to A is called as the condition of idempotency. So if your matrix is idempotent, then it is diagonalizable, that you can say. Okay, so this also you